Morning, everyone. I am Izn Ali. I'm a freshman at Newton South High School, and I'd like to thank ASIT for giving me the opportunity to present in this conference. Today, I'll be presenting to you some information on the mysterious callouts conjecture. In this presentation, we will delve into the origins of the callouts conjecture, explore the steps involved in the sequence, and discuss why this seemingly simple problem remains unsolved. We'll also examine how such a simple idea has continued to intrigue mathematicians for decades. And last but not least, I will present to you some examples and future applications in the modern world of science and technology. This conjecture, also known as the 3n plus 1 problem, is a simple yet mysterious sequence of numbers that has puzzled mathematicians for almost a century. Despite its straightforward definition, the conjecture has resisted proof or disproof, making it one of the most intriguing unsolved problems in mathematics. By the end, you'll see how even the simplest questions in mathematics can lead to deep, unsolved mysteries that continue to captivate researchers around the world. What the equation actually says. So the conjecture posits that if you take any number x and apply two rules to it, it will always fall into a loop of 4, 2, 1, 4, 2, 1, and so on. The two rules are, if x, the number you choose, is odd, multiply x by 3 and add 1. And if x is even, divide x by 2. Now you might be thinking that because 3 is greater than 2, this function goes upwards. Therefore, it'll never come down to 4, 2, 1, that way. So this is not true because half of the time, the number you start with will be odd. So then from there, after you apply 3x plus 1, half of the time that number will be, yeah. And then if you apply 3x plus 1 over 2 to the number, because 3x plus 1 is always even if you apply it to an odd number, then you can, half of the time, you will be left with a number that is divisible by 2, and then 1/4 of the time, you will be left by a number that is divisible by 4, and then 1/8 of the time, you will be left with a number that is divisible by 8, and so on. Now, if you start with an even number, then it's starting off divided by 2. Then half of the time again, you'll be left with a number that's divisible by 2, at 1/4 of the time divisible by 4, and blah, 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 blah. So if we sum all this up, then we actually end up with a function whose slope is 3/4, or -3, technically, and that trends downwards. So in the 1930s, all the way to like the 50s, they used to think that this problem was fabricated by Russians to stop US progress. And you might be wondering what that percent symbol is doing there. That basically means, like, if you have n% 2, it means n mod 2. What that basically means, if you don't know what the mod function is, it basically says that if you repeatedly subtract 2 from n, then you'll eventually be left with 0. And that's the definition of an even number. And n mod 2 equals 1 basically says, oh, you have n as an odd number. Because if you repeatedly subtract 2 from an odd number, then you're left with 1. So the Gauss conjecture, based in number theory and dynamical systems, has intrigued mathematicians because of its complex, chaotic behavior and the challenge it poses in proving or disproving it. A great example of its complexity is the uncertainty about whether 3x plus 1 over 2 results in an even or odd number. This is called parity. Say you take 21. Now, if you apply 3x plus 1 to it, you get 64. But then that's an even number, and divided by 2, it's still an even number. 32 is still an even number, and so on until 1. But if you take 27, then when you apply 3x plus 1, you get 82. But immediately, once you divide that by 2, it's an odd number, 41. So this is an example of parity because for 21, when you apply the rules to it, it's still even, no matter how far you go. And for 27, literally the second step is odd. So this is an example of parity, and problems with parity have been notoriously hard to solve. Anyway, an interesting pattern that should be noted is that when the log of this function is taken, and the linear example is removed, the resulting pattern looks a lot like the stock market. And this problem has even been used to predict what future stocks will look like. More on this on the next slide. People also haven't figured out if there's a wholly separate loop, like other than like every number comes down to 421, but they have figured out that if there is, it must be at least 186 billion numbers long, and no one's gonna use any time to find that. The Gauss conjecture, while primarily a mathematical puzzle, indeed has far-reaching implications across multiple disciplines, particularly in physics, computer science, and systems theory. Here's a closer look at how the conjecture influences these fields. The Gauss conjecture provides a simple set of rules, like divide by 2 if even, multiply by 3 and add 1 if odd, that generate sequences of numbers. The unpredictable nature of these sequences can serve as a model for complex systems in physics, where simple laws often result in chaotic and highly unpredictable behavior, like, say, a double pendulum. In thermodynamics, the concept of energy dissipation and how systems lose energy over time can be likened to the Gauss conjecture, like entropy. Each step in the sequence can be viewed as a loss of energy or progression towards a stable state, albeit in a manner that defies easy prediction, just like the Gauss conjecture. The conjecture of potential connection to chaos theory is notable because even though the rules are simple, the long-term behavior is highly sensitive to initial conditions and can result in unpredictable outcomes. This mirrors how small changes in initial conditions in physical systems can lead to vastly different outcomes. Like if you had a double pendulum and you stuck the second arm slightly higher, so that results in a way different behavior than if you stuck it 1 inch lower. And say you took like 30 and 31. Those two, their peaks, which is the highest number they reach, vastly different. Anyway, in computer science, algorithm complexity is straightforward, but determining the behavior of any sequence for any given starting number is very computationally challenging. And this highlights the complexity of certain recursive algorithms, even when their operations appear to be simple at first glance. And the iterative nature of the Gauss conjecture, where each step builds on the last one, parallels recursive algorithms, which repeatedly call themselves with updated inputs. The structure is fundamental in computer science and is used in various algorithms, from sorting to searching. And interestingly, the unpredictable behavior of the Gauss conjecture has also been associated with computer errors. Some computational models and error simulations use it to test systems' resilience. The seemingly random yet deterministic nature of the conjecture can serve as a model for these types of glitches and anomalies that occur in computer operations, especially when you're dealing with large datasets of complex recursive functions. And in chaos theory, small initial differences in input outcomes can lead to dramatically different outcomes, like I told you before. And the Gauss conjecture exemplifies this by showing how a small change in the starting number leads to vastly different sequences. And this offers insights into the nature of chaotic systems. This unpredictability, despite the deterministic nature of the rules, mirrors key concepts in chaos theory, where deterministic systems can exhibit behavior that seems random or chaotic due to the sensitivity of initial conditions. The Gauss conjecture is more than just a problem. It serves as a metaphor and tool, and its relevance in chaos theory, energy loss models, and algorithmic complexity demonstrates its broad interdisciplinary significance. I'd like to thank Asif once again. I will now take any questions that anyone has.
Very interesting and totally remote field of study. Is a biologist basically who is interested in medical science. But actually, if you try to, superficially interpret this theory, it's probably a very discontinuous number theory. And in biology, we have a lot of such systems. Just one factor for the slightly different. So in the last slide, you mentioned a chaotic system. Likewise, even if we don't really go that far, we have a very, multiple system. Let's say the genome issues or no, well, one factor really changed totally whether the patient will subsiding in the economic business, something stabilize or go really crazy and to the point of dying or losing the patient. Uh, this really question humanity with something. So I really encourage you to read pursue this very interesting concept. No matter what direction you go into, that will be benefiting your future. And thank you very much for choosing such a very, very simple but very intriguing questions. Just
You said in an earlier slide that the Kellogg conjecture can help like predict the stock market.
Yep.
How does that work? Like, because how does it show like future stock?
Okay, so if we put every number called hailstone numbers, the starting number of a sequence, on a graph, then there is a path that every single number takes. And so when we have stuff like this, we can average it and then we can apply Benson's law, which is basically something that's used to detect fraud and stuff because of how natural systems work. So when we apply the law, we can see that if the pattern does not match perfectly, well, not exactly perfectly, but like if it does not match closely with, say, like a specific part of any number, like hailstone numbers path, then we can see that there's definitely got to be some sort of fraud. And we can apply that also to the stock market because we know what's going to happen technically. So we can predict where the stock market is going to go without any other factors.